Okay, so today is lecture 3. So we're gonna do chapter 3. Just some quick announcements. They have been approved, or the university has approved the labs to be fully online if you wish. At least currently, we are still doing the half and half integration of in-person online. If for whatever reason you don't want to do that, you can contact your lab instructor and tell them you just want to do fully online. You don't need to give them a reason. You don't need to tell them you fear for your life or have a doctor's note or whatever. You can just tell them you just want to do fully online, and that's that. So contact your lab instructor if you're interested in doing that. Okay, so chapter 3, that being said, we will move along with this. I have just got the pen thing for my mouse here, so I'm moving this around with like a pen. Um, I'm not very good with it so far, but I can turn it into a pen or whatever and write things. So hopefully that is useful. I think there's only a couple keyboard shortcuts, so I have those down. But I'll write things as I go. Hopefully that'll be more helpful, and I'll be able to explain better. Okay, so what is this chapter all about? We're doing vectors. So with the vectors, remember we went over this before. They have both a magnitude and a direction. That basically is just the definition of a vector. And all this is just repeating the same things over and over again. The magnitude of it is called a scalar quantity. It's basically just a number, right? It's like the strength of whatever it is. If it's a vector like this is a vector. The strength is given by the length of the arrow, and then the tip here indicates the direction it's moving in. If we just got rid of the tip and we just drew a straight line, that is the magnitude. This is also a scalar, so it has no direction. So this means different things from a graphical standpoint and also from a mathematical standpoint, which this whole chapter is going to be mostly mathematical. I don't know if you guys have had a lot of this stuff in your math classes or not, but I'll go over everything the best I can. Okay, so they have these different terms, displacement vectors, and it's basically saying that a particle goes from A to B, A to B. And what we're saying is all three arrows have the same magnitude. Again, that they have the same length, right? So they have the same magnitude, same strength, and they're all going the same direction. In this case, they're all identical, right? This is what this is saying is that, again, you have a path from A to B, and we go there in 3 different routes, right? You go around from A to B in a squiggly line. There's a super squiggly line all around the edge. So yeah, again, you have these 3 paths to get from A to B, but the vector is actually just drawn from a straight line from A to B. The scalar and the direction, it doesn't actually tell you the path that was taken. It's just a mathematical convenience, really. So again, some of these, you have some actual paths that were written here. Again, you're only concerned with the vector that's been drawn, which is the scalar that's drawn here, and then the direction, which makes it a full vector. They have 2 displacement vectors. So basically your A to B is one vector, B to C is the second vector, and then A to C is the combination of those. You've added them together, right? You will also do this in lab down here. It's the same thing as this, but you're going to do this in lab when you do the vector lab. You have 2 vectors, A and B, and then again, you add them up down here. This is S. You can just actually, if you made this a grid, this is probably a terrible idea because I can't really draw straight lines with this. So painful. Hopefully you get the idea. If you make it some grid, then you can start measuring and say, okay, this point here, and it goes to here. So whatever, it's this amount of blocks. Then you can basically count how many it is. You can figure out magnitude. This is one way of doing it. Another way is if you were just given a number. You're basically given the magnitude right off the bat. But either way, if you have this, then it's easier just to draw a line. And when you do the lab, you have to do it 3 different ways. There's a graphical interpretation, where you aren't supposed to use the numbers. You're supposed to just graph it, and then you just use the numbers, and then you basically have nothing, and you're given just information, and you just use pure math to solve it. But yeah, that's all this is saying. There's a way to add them. Okay, so again, these are basically mathematical things that we're working on. Less physics, more the language that we're writing physics in. So one of the things is a commutative law. When the vector addition is commutative, which means you can flip the order of it. It's not a whole lot of new news, I guess. It also has the associative law. If you've been in some math classes, maybe you've heard of these things. So basically, these things can be rearranged. Again, that really shouldn't be new. So I'm not trying to get too heavy into it. But if you're unfamiliar with that, look at a math book. Look on YouTube for the vector mathematical property. So the negative sign then reverses the magnitude, right? So we can see that B is going up this way and pointing in this direction. So if we take negative B, they're parallel to each other, right? It's just going in the opposite direction. So vector subtraction, same deal. Some of the different types of vectors, and then we have another checkpoint that already has the answer on the slide. Okay, so basically, the question is saying you have 2 magnitudes, one 3 meters and one 4 meters. And it doesn't necessarily give you the directions of what they are. They do have a direction, but it's saying what is the max and what is the min possible if you were to add these things up. So if I look at this and I say, okay, this one's, we'll say this is the 3, and then I'll make this one a little bit longer, and then we'll say this one's the 4. Right, so this is your A and your B. So if you add these up, they go in the same direction, right? So you're going to have 3 plus 4 is 7, which is what we get over here in A. Now, if you made it go the opposite direction, now this is B. Now you basically just have to subtract them. So this is still 4, so you get the 4 minus 3, and it equals 1. So basically this thing can rotate like all the way around, right? And these are the most clear cases because they're going the same direction, so you're using the full quantity to add or subtract to it. If it was like, say, over here, and this was 4, and that's B, then you have to split the x and y components and only deal with the x and y components. And we'll get to that in the next couple slides. It was talking about the graphical method before, that's up here. So if we look at this again, if you see what's going on here, we basically have a vector that is the original vector B here is going this direction, and we've split it into the x and y components. So the x component you can see comes out to here, comes the same x distance, and then the y component comes down here, it comes the same y distance. Right, so you have this x component equals 7 meters, and then the y component equals 5 meters. So if you see this, and this will lead into the next slide, if you see this vector here, if we transpose it, basically just pick it up and move it, keep the same information, same direction, same magnitude, and we put it down here, we can bring it down here, and now this is b of x. So now we just basically took this vector right here, we brought it down here. You can see it makes a right triangle, right? So this helps you find some of the information of the x and the y component. And if I go to the next slide, you can see down here that we have the Pythagorean theorem, right? You have this x component squared plus this y component squared, and that's the square root. It's just the Pythagorean theorem written in the not the same as the traditional like ABC, right? So that should look familiar. Then you have the components, where in this case you have the x components and a cosine, and then the y components and a sine theta. Be very careful with always associating y with sine and x with cosine. This is not always the case. It depends on how you have your coordinate system set up, what direction you're looking at, like a multitude of factors. So usually this is sort of the convention that people pick, but remember that it is something that's picked, and this is not always necessarily true. This will become more of a problem when you start doing two-dimensional kinematics. The other one of the useful equations down here is the tangent. So you have ay over ax. This can be useful too. Okay, so it talks about sort of an introduction to three-dimensional stuff. So you have ax, ay, az. That's going to be the components of a single vector. It's just giving you the information for three of them. Then you have one of these checkpoint things. In the figure, which indicated methods for combining the x and y components of vector A are proper to determine that vector. So they're basically saying which one of these were drawn correctly. So if I look through them here real quick, we see that you have an ax and a ay vector. So you have the vector going here, the vector going here. The original vector was a, right? It's been split into its x and y components. The way it's drawn, the direction is this direction, because you have the tip of the arrow right here, right? So the way that this one's drawn is simply the wrong way, right? It should be drawn this way. So it comes over this way, and then it comes down this way. And then when you do the additional, the summation vector down here, normally you do it tip to tail. What I was always taught to call it, tip to tail. I think they call it head to tail in the book. But if you do tip to tail, this is basically tip to tip, right? So it actually doesn't work that way. So you always want to go from the tip to the tail, or the tail to the head, or like I said, however the book wants to put it. So this is going the wrong way. B, same deal. You have these vectors coming away from each other. All they did was flip the direction of the combined vector. So again, these are pointing away from each other. They should be basically going one direction, then going the other direction. C, again, your total A vector is right here. Its components, ax and ay. So now you're coming out here, coming down here. You go from the tip to the tail here. And that's correct, right? And it's labeled down here anyway. But same thing with this one. This one's correct. E is the last one that's not correct. So again, it's going up. These arrows are indicating that basically it's going the wrong direction. So you can see if you broke this into components, it's going this way on the y-axis. It's going up. And it's also going to the right on the x-axis. So these directions that they've added to these the graphical vectors are the wrong direction. And then again, this is in the middle, and they're showing basically the components here. So you would have to move one over to add them in the way they did it. That's why they have the little dotted lines. Okay, well, basic conversion. Your calculator can do this. Basically, you got to be careful whether you're doing things in radians or degrees, right? And you can flip your calculator if you're using a calculator. Even if you just Google this and you're not using a calculator, be careful whether it's in radians or degrees. The more you use these two systems, the more you'll get used to it. You'll just see a number and you're like, oh crap, this is in radians. I need it in degrees, or vice versa. But it's a simple transformation from one to the other, right? So you can just take your degrees, multiply it by 2 pi, divide by 360, and you get the number of radians it is. If you just reverse the algebra and go the other way, you can turn radians into degrees, right? But again, the easiest way is just to flip the calculator to make sure it's doing the correct way. This is your classic SOHCAHTOA. let's see if I can write that. So you get sine is opposite over hypotenuse, and then cosine is adjacent over hypotenuse, and then tangent is opposite over adjacent, right? So that's kind of the classic way of remembering what these three equations are. It's just SOHCAHTOA. I'm assuming they still teach that. So if you have your own way of memorizing it, whatever, that's fine. But you're going to use this stuff constantly. Constantly. So make sure you memorize this however you can. And here's some problems. I'll go over them later. This is still really difficult. I don't want to try to do problems with this goofy computer pen. Okay, so now we get into some more of the math. So they start talking about these unit vectors. A unit vector is basically this guy right here. And they give some information about it, like the magnitude is 1, it has a particular direction, etc. It's always labeled with a little hat. That's the little hat. And basically this is just giving you the information in a direction. So in case you don't have a direct graphical representation, it's broken down into these components. And in this case, it's 2 dimensions. It's I and j. If we look down here, you can see there's also a z that's in 3 dimensions. So it's not just ij, it's also plus, that's terrible, plus az k hat. So it's ijk, right? That's your classical 3-dimension components of a vector. So anytime you're dealing with this stuff, they use what they call like right-handed rules. That means you use your right hand. It doesn't matter if you're left-handed or right-handed, you use your right hand for this. You can devise your own way to do it left-handed, but everyone's going to do it the same way. They're all going to do it right-handed, so it's just more convenient to get used to it doing it that way. And I'll go over, there's a slide for that too. I'll go over that more in a minute. The quantities that they're talking about up here is the I component and the j component. They're vector components. And then they're talking about the thing that comes before that is just the scalar component. So basically you've broken this up into, this is the direction, and then this is the magnitude. So normally when you write this, it might just be like 6i, you know, plus, I don't know, 7j. Normally you're not going to have that little sub x and sub y. The information is embedded in the I and the j. That's telling you the direction. And then the thing in front of it is just the magnitude. So, where's this going here? Scalar components, and then we're starting some of the addition down here. So when you have this, if we have the same similar vector that we had, sorry, this is really hard to draw straight on. If I have some vector here, A, and I take out the components of it, I'm trying to separate it a little bit so it's not straight. And that one's definitely not straight. But basically you have the y component, and then you have the x component, right? So if you try to add these things up, they're not going in the same direction. That makes it basically impossible. So when you try to add these things up, you have this, we'll say 6 and 7, and then you add whatever the b portion is. You can only add basically the I portions together and the j portions together. And that's what it's saying down here. If you keep the sub x's, then basically you're adding up all the sub x's, sub y's, etc. It's just the opposite for subtracting, but you have to stay within the confines of the direction. And then another checkpoint here. In the figure here, what are the signs of the x components of D1 and D2? So D1, they're talking about what's going on in the x. So that's this direction. This thing is clearly moving up. So that's one component, and the other component should be right here. It's moving that way. So it's moving in the positive x direction, right? The second one is moving this direction also. That's the x portion, so that's also in the positive. and then the y portion is here. Right, so it's just positive, positive, which is listed down here. This says, B, what are the signs of the y components of D1 and D2? Well, we just did that. So the y component, the first one's going up, so it's positive in the y direction. The second vector is then going down in the y direction, so it's positive and negative. Part C, what are the signs of the x and y components of D1 plus D2? So you have to add these up separately, right? If you look at this, the x one's easy, right? So it's just, they're both positive, so it's going to add up to something positive. The y one is slightly trickier because you have them going in opposite directions, which means you're going to subtract them. But you can see that the first y component of the D1 vector is longer. So when you subtract this, there's still a positive portion here. So if you subtracted that piece from this, it would end up about here. So this would still be in a positive direction, and that's why this is positive. Hopefully that makes sense. Okay, so these are again, I keep kind of reinforcing this coordinate system. You set up the coordinate system for anything. And basically it's just saying it's independent of the coordinate system. And that's kind of just a broad generalized statement to be making right now. It's not going to make a lot of sense until you do some problems with it. But basically you're saying you have this piece down here, and we've just rotated it, this phi, this angle phi, we've rotated it that many degrees back so that the coordinate system of the primes here line up with the actual vector components of the vector. So maybe that's useful, maybe it's not. It just depends on the problem and what it's asking for. Okay, multiplying vectors. When you multiply any vector, you multiply it by some scalar, or not. You have to multiply it by some scalar, but in this case, we're going to start out by multiplying them by scalars. All you're basically doing is you have some vector, graphical portion again, and then we multiply it by some vector, and depending on what it is, it's just going to be same direction. It's just going to increase the magnitude. So if it is just a scalar, I'll try to do a little example here. Let's say the scalar is 6. Let's say your vector is ax plus by. Then this is simply just going to equal 6ax plus 6by. Right? It's just extending each of these things. So, because if you only extend one, you're changing the information, and that's not what the scalar is doing in this case. So, you need to multiply each component by the same amount, so they all increase proportionally. So division, basically same thing. Nothing new. So here's where we get into some of the names too. When you multiply two vectors, you have a scalar product that we call the dot product. I think it's most commonly called the dot product. That's probably what they're going to call it in math. That is what this is. So if you remember early in the semester, which was all of a couple days ago, I guess, I told you that I'm going to use this little dot symbol to represent multiplication. Again, you should have seen all this before, but I'm just kind of going over it for people that haven't. But the reason for this was because we basically lost this information. This is basically just saying that we had cosine of 0 previously, that there was no angle. So this just turns into 1, which is then simply a times b. Now we're going to start getting some of that angular information. Things aren't going to be as easy, so now you got to start adding the cosine portion into this dot product. So don't just magically forget about this and then say a dot b every single time is just multiplication. Again, the commutative law applies to this. So you can do the dot product here in the component forms. And again, they're saying that the I portion has to stay with the I portion. So when you multiply these things out, you're simply multiplying the I's, the J's, and the K's. And this is the most basic general form, right? So these things can become a lot more complicated. You could have something like, a whole expression in there, 2x plus 3y, whatever, multiple variables, that kind of thing. And then it has to be multiplied by everything that's in this B portion in the J direction. And this is more of what I just said before. Again, sort of more math rules here, nothing new. You have the projection of them, and you can see here that it doesn't matter which one is applied to. They just end up the same. Okay, so if the angle phi between two vectors is 0, the component of one vector along the other is a maximum. Right, we talked about this. So cosine, if you're doing that, is then 1. So also the dot product of the vectors, if instead is 90 degrees, which now you have cos 90, the component of one vector along the other is 0. So the dot product is 0. And remember, that's because we're multiplying it by cosine. So if you do cosine of 90, that's 0. So you're multiplying the whole thing by 0. So even if you don't remember these specific rules, just remember the mathematical rules of, what the different degrees of cosine and sine equal. Then we get another one of these checkpoints here. Vector C and D have magnitudes of 3 and 4 units respectively. I think that was the same as last time. What is the angle between the directions of C and D if C dot D equals 0? So that's what I just said. If you have cosine of 0, we know it equals 1. So that was what I was just saying. You have the cosine. So if it's cos 0, you're going to get 90 degrees between them. And then B, basically it's going to equal 1. So that's cos 0. So if it equals 12 units, you have 3 times 4. You have 3 times 4, right? And then if it's just 1, that means that this is cos 0. And that'll give you the positive and the negative. And then, of course, just flipping this 180 degrees, that flips the sign, right? Okay, so now we have the vector product. What's more commonly called, I would say, is the cross product. That's definitely the terminology we use, the dot product and the cross product. So if the dot product is multiplying a scalar times a vector, the cross product is multiplying a vector times a vector. And it works a little bit differently, right? Because you're dealing with more information, you have more directional information, not just a strict number being multiplied to a whole vector. So again, for this changes. You now have sine instead of cosine. And we need to start using the right-hand rule. So, and there's a little star thing down here, basically saying if A and B are parallel or anti-parallel, meaning this is what they're calling anti-parallel, and then this would be just regular parallel. So basically, there's 0 degrees difference between them. They're parallel, but they're just going 2 different directions or the same direction. If A and B are parallel or anti-parallel, A cross B equals 0. Right? There's 0 degrees of separation for them, so now it's sine of 0, so the whole thing equals 0. And then same thing, it's a max when it's perpendicular, right? So when it's like this, so now you got 90 between them, so it's sine 1. Or is equal to 1. Sine 90 is equal to 1. Okay, so this is hard to do because you can't see me. It's much easier just to show you and have you practice it. But this is important. I know this seems kind of goofy, but you're going to use this a lot, so I would practice this. Basically, the gist is, if you can see where my cursor is, whatever it is, if it is A cross B, whatever the first thing is, that's what you start with. So if it's A, start with the A vector, and then you move to the B. So usually you just close your fingers around your hand, right? And that gives you the direction of your thumb. That's telling you like what's basically what's going on. So I won't get into that so much. The right hand rule becomes more complicated, and we start using different fingers, and then we add a thumb, and you can tell when it's positive and negative. So yeah, don't worry about the rest of this stuff. Just basically A cross B. You're going to start at A, cross to B. When it's B cross A, then it's the opposite, right? So you got to start at B, and then you cross around this way. Draw little arrows. You're going to cross around this way to close B cross A. You cross that direction, right? And then it's pointing down, usually meaning negative. Okay, so unlike the dot product, the cross product is not commutative. So if you switch the directions of these things, as we just stated before here, if it is A cross B, it's positive. Your thumb points up, indicating positive. If you do B cross A, it's then negative, right? So that's what this is saying. If you do B cross A, that equals actually the negative of A cross B. So you can't interchange them and get the same result. When you're doing this you're going to do in a matrix, right? I don't know if you guys remember matrices or not. Let me see. They expand it down here. I will try my best to write this out, but basically you'll have I, J, K portions. And then within that I, J, K portion, A, we have AX. AX, AY, AZ. And then that's going to be crossed with BX, BY, BZ. Right, so hopefully this looks familiar and you've done a matrices before. If not, you better start getting real used to it. Again, this is something else you might have to look up separate videos on and practice, but there's sort of a standard method of approaching this. So if you notice down here, this is the expanded form of these. So if you want to know how you multiply these, you would start with AY and you multiply that by BZ. So you go this direction. I don't know. I don't have an undo button. So basically you go this direction, right? Which is labeled here. So you got AY times BZ, AY times BZ. The second way you go to BY and then you go to AZ. So you cross these two right here. This direction, and this is what you always do first. The second portion, the way that you should be taught in class, should be AX times BZ. So you're doing basically, you're starting out, you're doing J times K portion in a cross fashion, and then you're doing the I portion times the K portion in a cross fashion. I don't want to draw too many lines on there, it'll confuse you, but if you do it the way that at least I was taught, you do AX times BZ, and then you go minus, because it's always minus inside the parentheses. You then do minus BX minus AZ. You can see they didn't quite do that. They did it backwards. They did AZ times BX, so they're just going the other direction. And all that does is allow them to eliminate this negative sign. So if you do it the way I just said, going from left to right, you would have a negative sign in here instead, and that would be distributed to the things inside. So they just went the opposite way to get rid of it. And then the last portion, the K portion, is then you take the I portion, basically cross with the J portion, and you're doing AXBY, which is down here, and then you do BXAY, right, which is down here. Again, if you've seen this before, hopefully that helped jog your memory. If you've never seen it before, you're probably like, what the hell is he doing? Just look up some of the multiplication with matrices. Checkpoint 5. Vectors C and D have magnitudes of 3 and 4 units respectively. Again. What is the angle between the directions of C and D if the magnitude of the vector products C cross D is 0 and 12 units? So same deal as before. You're basically just doing 4 times 3 times some sine. So if it is sine of 0, then this becomes 0. So the whole thing equals 0. If you do 4 times 3 times sine theta again, and it has to equal 12 units, that means that this equals 1. So it must be sine of 90. So you just get what you started with. You get 4 times 3 times 1, and you just get 12. There's some more book problems. And that's it. So this one is, I don't know about straightforward, but this is actually, you should have seen most of this stuff before. This is probably just the first time you're actually going to use it for something outside of math. For me, when I was younger and I went through math classes, I didn't understand math at all. And my biggest hangup was because it wasn't actually applied to anything. And physics was super helpful to me because it helped me make sense of what math is and what the purpose of math is, because it gave me something that was actually applied to and used for. So yeah, go over your math, get good at this stuff because you're going to use it a lot.